So on our next to last class, we want to, in scientific computing applications, we want to look at data analysis and the most important purpose for data analysis, which is pattern recognition. And I am using a set of PowerPoint slides provided by Dr. Stephen Ratchford, who presents some quick detail to ECS scholars during the summer. Do we have any ECS scholars with us today in class? Former ECS scholars from previous summers?
Yeah, I did ECS.
Yes.
Okay. So if you managed to catch Dr. Ratchford's presentation on statistical analysis or statistics, what we want to do is just call out some specific concepts. And he provides one of the most efficient and concise explanations about certain statistical methods that I've seen anywhere. And so I just wanted to give credit where credit's due. I'll post this information along with the study guide, and the study guide will be out shortly. We do have a number of assignments. So we have 3 assignments basically. We have one that concerns standard deviation. So we're going to have a short review and some related resources, and then an assignment where you perform standard deviation. And then a second assignment that has to do with an ANOVA test and a whisker plot. So we want you to be able to run a quick ANOVA test and create a whisker plot. And then we want you to be able to step through the creation of a traditional linear regression. So we want you to, and as I've done before, I'm going to be providing a YouTube with steps and inputs. So basically what's going to happen is that you'll have an assignment document and a rubric, so you can score your own. After you finish, you can check to see, do I meet the criteria for this assignment? And it's going to show you exactly what it is you should have. So the video is going to show you, the screenshots are going to show you, and the rubric is going to show you, do you have, and I provide the data that you need to start with, so you don't have to waste a lot of time with data input, right? You're not spending half an hour just getting the stage set, putting all these numbers in. All you're going to do is import. So we do have the 3 assignments, and then we have a solution. For the solution in Module 4, I'm considering making it optional, where you have a choice. You can do a Monte Carlo simulation, right? Or you can continue with the Access database with the auction data. There's some data mining that you can, you basically, whenever we talk about data mining, we're talking about complex queries where you query the queries. You continue what we did for the solution in the last module. You may not be all that jazzed about working with data and Access any more than you have to this point. And so I think what you'd rather do instead would be the Monte Carlo simulation, where you're going to generate some random numbers and then project a result with Monte Carlo methods are also used with things called Markov chains. So that's another predictive or simulation method. And I just wanted you to understand what's coming ahead. So once again, you'll have a choice between what you prefer to complete for the last module solution. It's not module 5. I have some reorganizing to do here on the screen and in Blackboard, but you'll have, once again, to summarize, there will be 3 assignments, a quick one on standard deviation, an ANOVA test and a whisker plot where you build that, and then a linear regression that you perform. Then the solution is your choice of a Monte Carlo simulation or some data mining where you continue the access database that you created for the auction data. Are there any questions about what's expected between now and the end of classes next week? Any questions?
So you said it was 4 assignments and a solution?
No, 3 assignments and your choice of a solution. 3 assignments and your choice of a solution. Okay? And I think the best way to learn about the concepts, so are you going to have a ton of stuff to read? No, this is more hands-on. The last module is more hands-on. You will not have as much material to review in terms of reading, but I will have some things for you to watch in video. Okay? So, yeah, let me clear the rest of this. All right, so when we talk about scientific computing applications, it's really framed with this idea of the scientific method. And so you have these observations and you have a question, a research question, right? And you may have ideas, more than one idea, about answers to those questions. And in general terms, by extension, if you have more than one idea about a potential answer to that question, you should be able to predict, based on your answer, what would happen if you tried something. So you're inferring that if your idea about the answer is correct, you should be able to try something in an experiment and confirm or infer that the result your answer suggests is accurate. Dr. Ratchford had a much more elegant and straightforward way to explain that. But the point I'm trying to make is that there's a lot of confusion between scientific method hypotheses and statistical hypotheses. We'll get into that more in a minute. But most students are familiar with the idea of the scientific method, and that you have a research question, and then a hypothesis would be a single answer about that question. If you have more than one answer about that question, you might have multiple ideas. You can infer based on those answers how to test for that answer. You can infer based on those answers how to prove your ideas. And that leads to the design of experiments, right? And then you carry out the experiments. I will say that one of the most important aspects of scientific computing applications is keeping a log or a journal of your process. So as you're walking through this scientific method, one of the things that's very common about the scientific method and scientific computing is that you're doing a lot of repetition. You can, especially in living systems, the variability of experimental results, when you're doing your experiments, you can get a lot of results that vary quite a bit. And so the ability to repeat an experiment over and over again is critical. I would say a lot of times when people cannot share their outcomes with others. You know, they go to a conference, they publish their results, and lo and behold, everybody gets excited, and there are dozens of other scientists, other researchers around the world that start trying the same thing. Well, if what you shared was simply statistical and the data outcome and not the methods, right, the qualitative aspects, you know, what instruments did you use to make your measurements? What environment did you collect the samples in? You know, what time of day, what voltage levels applied for this type of circuit or whatever. If you don't specify those things and collect those things later on, when other people are trying to duplicate results, because you can get a variety of results, you want to be able to report the findings for critique, because if you're successful, people are going to try your ideas out. This is how the world's changed, right? So Madame Curie and her husband started messing around with radium, not radon, that's a gas, radium, and discovered X-rays and discovered how you can expose someone's tissue, body tissue, in front of a photographic film with a radon sample, radium sample, and the radium sample would etch an outline on the film, and then you could see the bones, right? Of course, Madame Curie's husband died because he didn't understand that radiation would kill you if you got too much of it. They didn't understand some things back then. But they reported their findings, and then everybody else tried and repeated. And the basic point I'm trying to make is that much of the problems people have with reporting their findings and then receiving critiques in the aftermath, you know, everybody thinks, well, the standard deviation should match. The statistical methods are very precise and very, everybody seems to agree how to conduct the data analysis. What often varies are the data collection and how the experiments were performed. So I don't, despite the fact that this module is about data analysis and pattern recognition, one of the things I want to intentionally call out to you is that there's an aspect to repeatability that has nothing to do with data analysis. It has nothing to do with the statistical pattern generation. It's not, I mean, but it's important because it's the foundation that allows for others to confirm the findings. And if they're using the same statistic, if they're using the same data analysis and the same statistical methods, and they can't duplicate your findings, then you're all wet. What you've done is reported, you know, life according to you, and it's nothing other people can work with. So, all right. Are there any questions about the scientific method and the importance of keeping a log or a journal?
No, I think I understand that.
Okay, so
pretty
that's
well.
so that's the largest qualitative aspect. That's the largest qualitative aspect of this module, is just, you know, don't forget the legwork and the, you know, the just good old-fashioned due diligence. Record everything, take notes on everything, everything that led to your data. All right, the rest of the time we're going to be talking about the data analysis and the pattern recognition. Okay. So one of the things that is important to emphasize about a hypothesis is that it's not an educated guess. People make an informed guess or an educated guess. They read up on things, they get some concepts, and then they take a guess at something. And that's not the same as a hypothesis, right? So a hypothesis is something that you're supposed to be able to test for and run and design experiments with. So once again, a hypothesis are possible answers to a question. They should be mutually exclusive and complete, meaning they're very discretely defined, very tightly defined. And you want a plain answer. You can get very statistically sophisticated. That's not the goal. The goal is to be able to say yes or no to a certain answer, right? You want to be able to prove, you want to be right. So when you look at these differences in hypotheses, some are very tightly defined and some aren't, and Dr. Ratchford went to the trouble to emphasize how important it is to state your hypotheses in concrete terms. So here's one example. Can people tell the difference between Coke and Pepsi? There is a difference between Coke and Pepsi sugar content. There's a difference between the fizziness of the two sodas. People are misled or swayed by their own style or affinity for certain styles of advertising. So when we're dealing with pattern recognition, what we really want to do is analyze the data that results to the point where we can work conclusions. And as you're predicting about your answers and you're drawing inferences about what you think will happen next, you design a test to conduct and some data to collect. And so once again, he's got other examples here. Roosters crow because they're hungry. Roosters do not crow because they're hungry, right? And so you could get hungry roosters and well-fed roosters, and then you could measure how many times they crow. So this would be a prediction based on a hypothesis about the roosters. If your hypothesis was one versus the other, you could predict what would happen if you had a group of roosters that were starved versus a group of roosters that were well-fed, and then you measure the number of times they crow, right? So this is an example of how you extend a prediction from the inference about your answer, your hypothesis, and then that leads to measurement. So you have variables, and what's important to understand about the variables is that normally distinguishing which ones are the constants or the controls and which ones will be manipulated are important. The control variable is typically the independent variable, and the one that's manipulated or changed is the dependent. So you identify a dependency, and identifying which variables you're going to work with is really important. Now, he's asserted repeatedly that you have lots of variation in responses, and you have to be able to repeat the experiment many times, but that's true in a number of STEM disciplines, especially cybersecurity, especially computer science, especially technical disciplines, physical sciences. You've got to be able to do that over and over again. You can work with whole groups of results. And so you'd have a control group where everything was normal and you study it, and you have another group of individuals where you collect data where you're varying some of the conditions or circumstances. So I'm going to click through here. Statistics. All right. So when we're trying to understand data and we're trying to identify patterns in data, when we say data analysis, the primary discipline we're thinking of first is statistics. Do we have anyone in the class that has already taken a statistics course? I think it's math. Is it Math 235? Isn't it MAT 235? Statistics, is that correct?
I don't know. I've not taken statistics.
You have not taken statistics. Okay. Depending on your major, it is a requirement. I know for computer science, it is required if you're in marine biology, I think. It's also required. But there's also statistics for biology majors. That's 245. Anyway, the point is that statistics, there are two main, I don't want to say data types, okay? So when we talk about data information that we apply analysis methods to, I want to be intentional about saying, when we say data types, we're talking about things like integer, floating point, string, real, Boolean, those are data types. But in terms of the two different kinds of statistics, there's descriptive statistics. So there's data analysis that's descriptive, and there's data analysis that's inferential. That is not to be confused with data types that have to do with the type of digital information it is, right? Does everybody understand what I'm saying what I mean by that? So if we're talking about raw data, you have data types like string, integer, floating point, Boolean in a database. Those are data types. If you talk about the types of data analysis, the types of statistics, there are two main camps, descriptive and inferential. So descriptive is when you're working numbers. Inferential has more to do with probability. The simplest way to understand this, descriptive has to do with quantitative aspects, quantitative analysis, and quantitative pattern recognition. Things like mean, mode, min, max, average, standard deviation, all that kind of stuff. Inferential would have to do with the probability of correlations between two data sets or two populations. So this one centers on probability. This one centers on number crunching. Is that a clear way to describe this?
Yeah.
Yeah.
I understand that.
Okay. So when you want absolutes, which one am I talking about? Descriptive statistics or inferential statistics?
Wouldn't it be descriptive?
Yeah, exactly. If you need an absolute, what is the standard deviation of these measurements? If you need an absolute value and you need a number, if you're talking about something that centers about numbers, that's descriptive. If you're talking about, gosh, we collected samples and we think that there's a positive correlation between this population and that population, and the probability of a relationship in data outcomes, that's inferential. So if we think of probability, so this one is not absolute. It's really important to explain that when you're dealing with initial discovery work in the scientific disciplines, some of this stuff you're doing a lot of heavy measurements in basic science, but then when you're trying to draw conclusions, you shift a gear and now you're in the inferential territory, and there's a probability factor. It's not an absolute, and you have to be careful how you state your outcomes. I'm going to say that one more time. This one you can claim up and down and take it to the bank. This one you have to be careful about how you state your outcomes, because they are not absolutes, and you cannot, like, for example, if you have a correlation is not the same as causation. So when the sun is shining more, my solar panels are generating more electricity. causation in that scenario is easy to identify. But there are plenty of situations where we don't know if the relationship is that clear or that plain. What would be a good example of this? People who fight a lot have high divorce rates. And let's say that they come from families with high divorce rates. So if you come from a family, is it that people who come from families with high divorce rates fight more often because that's kind of how they were raised and that was their upbringing? I mean, I'm talking about like a social sciences, psychology, sociology study here about conflict in marriage and divorce rates, right? If you were doing a study on that, those kinds of things are much more vague, and you have to. It's hard to pin down what came first, the chicken or the egg. So whenever you have conditions of a study where it's hard to determine, just remember the two distinctions here and which case is better to use. So if I have something that has to do with probability, I'm dealing with inferential statistics. If I need to measure the absolutes about the numbers, I'm dealing with descriptive. I know I've kind of beat that up here. So you have two different kinds of data. You have discrete data and continuous data. And so instead of using data types, I'm steering away from the term data type again. I'm going to say you have two different kinds of statistical information data, right? So when we're talking about statistics specifically, not databases or programming, in the statistics world, you have discrete data, which is basically broken out into very clear categories. So the birth of baby girls by month, the months of the year are categories in terms of the calendar. So it's not the Julian date or the number of days into the year where the baby was born, it's the month. Then you have 12 discrete months, January, February, March, April, May, June, July, August, September, and the rest. That is discrete data. So if you're indicating on a data collection sheet what month was the baby born in, the baby girl was born in, you're going to say that's a discrete type of data. It's a discrete kind of data in statistical terms. In terms of programming and database logic discussions, whenever I talk about data types again, I'm talking about integer versus floating point versus numbers with a decimal point versus. All right, so continuous data. Statisticians say that if you're dealing with continuous data, it's a range of possible answers. There's no discrete category, so you have 365 days in the year. And if you measured when female babies are born by the given day of the year, from 1 to 365, that's more like continuous data. So measurements, lengths, weights, something. Now you can basically have a range of measurements or continuous data that you decide would be a certain category, and what you're doing is converting those into another form of discrete data. But it's important to understand the two different kinds of statistical data, because you'll see in a minute, you can easily select which types of statistical analysis you should use to discern patterns, right? If you're doing pattern recognition, you want to analyze it. In a lot of data that's collected, natural data, in natural systems, there's a normal distribution of the data, and What that means, everybody's heard of a bell curve. So you have this typical pattern of distribution. And if you talked about the height of individuals in the US Virgin Islands, you have a lot of people that fall within a certain height range. And then you have some very, very tall people and very, very short people. That was the example that Dr. Ratchford used in his demonstration here. The thing about normalized data, you have variation. So whenever you have these natural populations and you have variations of data, you have this what's considered a normal distribution. What's normal for certain data sets or populations can change. So the distributions look different depending on what you're talking about. But in any case, when there are variations from the typical measures, those can be defined as standard deviations from the mean. And so there's this consistent way of breaking out whether or not something is within the norm or outside of the norm based on where it falls on the chart. And in classical statistical analysis terminology, a standard deviation is a useful method of data analysis because it helps you understand if something is within range or out of range, if it's considered normal or unusual. Are there any questions so far about this?
No.
No?
Not yet.
Okay. We had a couple of students join us a couple of minutes into class, and I asked at the beginning of the course if anyone had already taken the statistics course. So among the 8 of you, has anyone had the Math 235 course yet?
I took statistics already, but that was probably maybe 3 years ago.
Okay.
I took it too. I took it over the summer.
Okay. All right. Well, I'm oversimplifying here because I'm summarizing for the basic purpose of some of the hands-on we're going to be doing. So please don't hesitate to step in if I'm explaining a slide and it's not on point. I'm trying to stay out of the weeds. I don't want to overcomplicate. You can get an entire PhD in statistics, so it is a very highly advanced discipline. And what we want to do today is to cover some essentials about it. So here's an example of how those how the normalized data can vary depending on the population or data set, right? You could have a very tight bell curve or a very flattened bell curve depending on what you're studying and the criteria for measurement and a whole variety of factors. The important point to understand is that standard deviation helps you gauge whether something falls within what's considered to be norm or outside the norm. And generally speaking, if you're within the 2 standard deviations, so if the mean is this line here in the middle, within 1 standard deviation, you're in this first section or the section above. So that's within 68% of the population fits within that range. And then in classical terms or classical definition, if you come out two standard deviations, you come out another layer. See, what is that? Another 28%. Most of the population fits within this range, and anything outside that range would be considered a result that varies significantly, right? So you have an outcome that's notable because it's not within the normal range of results. I hope I'm doing that some justice. So yeah, variability, there are much more granular ways to express variability. So range is one of them. Variance is another formal way to do this. Apart from standard deviation, you have a standard error of the mean and something called confidence interval. Whenever we're talking about numbers-based data analysis like mean, mode, variability, and the shape of the curve, that fits into this generic category we call descriptive statistics. And then, as I said before, the inferential statistics has more to do with probability. So you're always looking, when you're analyzing data for the purpose of inference, you want to understand if two or more data sets, and I'm gonna use the word data set here. Dr. Ratchford is usually studying lots of populations of living organisms. So in his wheelhouse, the term populations would apply, but in my area of expertise, we're talking about data sets, right? You're trying, if you can determine whether two data sets are different in some aspect, right, based on some criteria, or if they're related, right? So they're either different or they're similar. The whole point of inferential statistics is to establish that they are different or establish that they are related or similar. There's a connection. There's a relationship. So what's the flip side of an inferential, what's the flip side of these two cases? Well, they're totally unrelated. You have a case where there is no relationship. They're neither different nor related. When you analyze with inferential methods the two populations or data sets, you find out that everything's all over the map. It's just random. And so to illustrate what we're talking about, if you were talking about the length of hair between males and females, right? And we said that green is female, they have longer hair, and blue is male. You have some females that have shorter hair, and you have some males that have longer hair, and so there's some overlap between those populations. If we talked about another characteristic, they might be more related. What you're trying to establish with inferential statistics is either that two data sets are distinctly different or that they're distinctly related. And what you're trying to establish is either of those cases. You may run some inferential statistics only to find out that they're not related at all, right? They're not. So Dr. Ratchford had a demo that had to do with numbers inside a hat, and he asked students to predict if the numbers inside one hat are bigger than another. And for the sake of illustration, as you click through the mouse, let's see if we can do this here real quick. So as you click, if I ask you to vote which hat has bigger numbers, and we pull a couple of numbers out and we start doing sampling, some of you, if you were to decide right now, might say, well, the hat on the right has higher numbers. But in real life, when you're doing experiments, what could be the case is that you have two hats that both contain numbers 1 through 50. And as you're clicking, they're randomly pulled from here. And so you're trying to conduct a study to see if there's a relationship or a pattern, whether they're the same or different. You want to establish an inference about patterns. And as you continue doing this, you find out that there's some overlap, right? So In this example, the 9 on this side, up to that point, the 9 is smaller than the 10 over here. And in general, what you want to do is make sure that you can clearly establish that there is a distinction or a difference between two data sets that's notable, or there is a similarity or relationship between two data sets that's notable. And when you conduct inferential analysis and all you get back is random, that's called the null hypothesis. So there are two cases for statistical hypotheses, and once again, these are statistical hypotheses, not science experimental hypotheses. We're not, we don't have a question we're trying to provide an answer for. This has to do with the number crunching. So as we're doing the data analysis, if something is related, if there's a difference or a similarity because of a relationship, and that's an inference, that's called a working hypothesis or an alternative hypothesis. And but quite often when you do inferential analysis with statistical methods, you find out that there is no relationship. So everything's just all over the map and it's completely random, and they're two completely unrelated phenomenon. When we're dealing with statistical error, there's this sensibility of P for probability. If it's 0.05, that's considered an acceptable level of error. And the key takeaway for this is most statistical error that people try to determine is the type 1 error. Very few people actually run type 2 error on their statistical data. The thing that we want you to understand is that if this number is less than 0.05, then there is a stronger probability that there is some kind of relationship. Either the two data sets are different or the two data sets are related. If there's a completely random result, then this number is going to be higher. Now I'm greatly oversimplifying the explanation of this value here. The other thing too is that this is just a standard number that statisticians use in gauging the level of error for their probability calculations. You're going to reject the null hypotheses. So what we're saying is you're going to say, no, this isn't random. If you see 0.05 or less, the conclusion you can draw from type 1 error is that you don't have a random inference between the data sets. They're either different or they're similar. Then again, you have to be careful about your conclusions. I'll explain more about that in a minute. All right, so for some of these statistical tests, some of the analytical methods include chi-square, t-tests, ANOVA, and then you have multiples. So an ANOVA is a multiple, it's like a set of miniature t-tests. And then you have multifactorial or nested ANOVAs. So if you have several variables that you're trying to gauge simultaneously, and then regression, right? Or correlation tests. So whenever you're doing a regression analysis, you're identifying some things. Now, the important thing I want you to get from this session is that each of these statistical tests are best suited based on the kind of data you're working with. Well, what are we saying? So we were talking about variables, and the independent variable, the one that's held, the dependent variable is the one that's changed, or you suspect is changed as a result of this variable. So the independent variable, if it's a discrete kind of data versus a continuous kind of data. So once again, I was very excited the first time I saw this explanation by Dr. Ratchford, because I thought, this is so cleanly broken out. So he calls this his statistical test cheat sheet. And we're going to use this in our class. So what do I want you to be able to do with this image? And I'll capture this and put it in the study guide. Based on a scenario, if your independent variable is measured with a kind of data that is discrete, like sex, male or female, months of the year, right? If they're categories of measurements and you're just marking which type or category is being used, that's the discrete kind of data. If you're dealing with something that's measured with a scale and it's not cleanly broken out into categories, rather it's a continuum, right? That's continuous. And so basically here you see that which statistical test is used in which case. You are going to perform so your assignments, we said when we started the session, you're going to do a standard deviation, right? Then you're going to do an ANOVA, you're going to run an ANOVA test, right? So I'll have some data and a walkthrough and a quick assignment. Whisker plot. So I want to go back to this. The whisker plot. When you look at a whisker plot, it's a clean way of graphically representing the range of data values and then where most of that data is placed. It's like a miniature distribution curve, graphically speaking, and I'll show you an example of that in a minute. But the important point is you're going to do a standard deviation, you're going to do an ANOVA and a linear regression. We want you to try each of those on for size so that you're familiar with what those do and how they work. The thing that I want you to understand is that when you have continuous measurement and continuous measurement, when the data, the kind of data you're collecting is continuous in nature, it's not discrete and broken into categories, then you're dealing with a regression analysis. It's one of the most common go-to methods of data analysis for that kind of experimental data. When you have a discrete variable and then you have the dependent variable is continuous, then you're dealing with one of these two types of tests. One of the examples that he used in a previous presentation was whether the circumference of the trees are greater on the upper campus than the lower campus. So he had a scientific study where he said, let's compare the girth or the circumference of the trees, how thick the trees are. Are the trees thicker on the upper campus of the UVI grounds versus the trees that you find on the lower campus. And there's this notion that, one of them has more rainfall, or maybe the soil is better. So you just want to understand that. If you're measuring the girth or circumference, that's a continuous measure. The independent variable is the concept of upper and lower. So as you're collecting data and you're measuring, the tree is either on the upper campus or it's on the lower campus. So which type of campus, that kind of data is discrete data. It's either upper or lower campus, but the measurement around the trunk is continuous because you're using a tape measure. And you're not measuring anything other than the girth or the thickness of the tree. You're not measuring how green the tree is. You're not measuring how old the tree is. You're not measuring other aspects of the tree. If you had other aspects of the tree you had to measure, then you would use an ANOVA test instead of a t-test. So here is a good, so when I talk about whisker plot, when you're graphing your results, oftentimes when you're using, well, and this is just one representation, but you see the line. So this is the range of data values that were collected. And yeah, this isn't the best graphic to explain what a whisker plot is, but superimposed over this range of data is a shaded area that shows you where most of the normal data resides. So if we were to slide this shading up so that it was on this end of the line, you'd say, okay, among all the data samples that were corrected, this was the max and that was the min, but most of the data samples were here, right? So a whisker plot is kind of a combination bar graph, data normalization curve, and range representation. And it's actually very cool. And I'm hoping that after you have a chance to see it and work with it, that it'll be something that you use commonly, because everybody gets to see a lot about your data in a glance. It's very, very helpful. So whisker plots are very, very helpful. I asked College of Science and Math faculty which statistical methods we should cover in this class. And linear regression, ANOVA, and whisker plots were the three most common answers I got back from my colleagues, your other professors, which is why we have the three assignments based on those three things. That's all we wanted to cover for today. We just wanted to give you some essentials about data analysis, the different types of data analysis, inferential and descriptive, and some specifics about each and where they might be used and how some of those methods are useful. Are there any questions before we clear for the day?
I
No.
don't have any questions.
Just the module 4, is that, can we view that on Blackboard right now, or?
You'll be able to view it before the day is out.
Okay, sounds good.
And I'll have some of these resources out there as well. And I'll also start posting some of the assignments.
All right, well, appreciate that. Thank you.
Yes. Was this a class that voted to do the retakes right before the exam or right after you took the assessment? I thought you all voted to wait until the exam.
No, I think we were expecting the retake. Like a lot of people, like someone was talking about it last class, if you were gonna post the retake. Well, not the retake, the reconciliation. So
Oh, the
my point
reconciliation.
might be void.
Yeah. Reconciliations are always there, but the alternate version, I think it's only the operating system class. Yeah, never mind. So what am I going to do? Let's talk about the calendar here real quick. This is the last day of class, so I have one other class to review things for Module 4 with you. This is a study day. You'll have a couple of assignments to do between now and then, okay? And then the third assignment and solution. From here on out, starting with the study day, you're going to have retake. You're going to have availability to retake any of the assessments as a way of studying for your final exam. When the final exam is scheduled for this course, it'll be posted during exam week. So this is exam week here. But you'll be able to retake any of the assessments to help you prepare for the final exam. And even though the final exam will be posted on the day it's supposed to be available, I'm going to leave it open until the 5th of December, 11:59 p.m. So what am I saying? I know some of you have to take the final exam when it's scheduled because you have other final exams later in the week. And so you're trying to plan your week, and I respect that. And I'm going to honor the system that's in place. So whatever day this class is supposed to have its final exam out there, I'm going to make it available to you. But you are not obligated to take it at that time. You have, I mean, after we finish our last class here, you have the rest of this week and then all of exam week to, review and take the alternate assessments on the modules and to study up. And you have until 11:59 p.m. Saturday to take your final exam for 239. Are there any questions about what the expectations are to finish up our season?
I have a question.
Yes.
There was an assignment that was labeled as option. So I thought I didn't have to do it, but then I got a 0 for it, and it said that I can just complete it whenever. It was way back in module 1, so I can just do it and I'll get the credit for it.
Yes. I'm gonna, okay, so I'm also gonna open up all of the assignments. So if anybody wants to complete something they hadn't done before, everyone will have access to any unfinished assignments or solutions.
Yeah, it was just something about the disk defragmentation. I normally take care of my computers, so I didn't feel the need to do it.
Right.
But I didn't know if I had a grade attached, so I don't like to get that 0 for no reason. So
Well, if people did it, it would mean their virtual machines would run smoother and more reliably, and so there was a built-in benefit for that activity. But I didn't require it because, I mean, how does a Mac user do a defrag? And
that's true. That's true.
they install something or uninstall something, and then it does it automatically. That's how they do it. But
So is it something I need to do?
if you want extra credit, that's one way to pick up some more extra credit.
I'll take it.
Yeah, I mean, that's why we have extra credit. Now, I mentioned this. I said your solution, you'll have a choice. Yes? Did everybody hear that?
Mm.
So for the solution for Module 4, you can choose either a Monte Carlo simulation or some data mining, right? So you can continue the auction data work process, or you can do the Monte Carlo thing. I can post both and then say to everybody in the class, if you want extra credit, you can complete both solutions. I mean,
Okay.
both of them might take an hour. If you watch the video, you read up, and then you start, it usually takes people about an hour to complete them. So it's
That's not bad.
no. And this material for your last module, there's not a lot of reading either. Very, it's just sticking to the basic concepts that you need to know about data analysis and the types of data analysis. So So if you have a little extra time, it's easy for people to log additional credit just by completing the second solution. So I'm going to put them both out there. If you complete both of them, I'm going to assume you want additional credit. And I'll score them both.
That sounds good.
Okay?
Yeah.
Yeah. So, and if you get, let's say you only get half the credit on the second solution, well, it's not like you're losing points on your grade. You're just picking up extra points for the average. So it won't count against you. It can only benefit. Does that make sense?
Yes.
Okay. Any other questions? All right. Well, thank you for asking that. And we'll see you next Tuesday. Have a great weekend.
All right.
All right, see you next Tuesday.
See you guys.